Module 4, Lesson 26, One-Step Equations, Addition and Subtraction. I can use substitution to determine whether a given value makes an equation true, so we're going to check our answers using substitution. And I can write and solve equations and inequalities involving real-world problems. That comes in a little bit later in the lesson. I can solve one-step addition and subtraction equations by relating an equation to a diagram. So we are going to be using tape diagrams to solve these problems. We want to have that deep understanding of what's happening. So I know that some of these you're going to look at them and you're just going to know the answer. Take the time to diagram what's happening. And then we're going to use substitution to determine if my solution makes the equation true. I already said it, I'm going to say it again. Most of the equations we are going to find solutions for today, or solve these equations, we can do them with mental math. We probably have them memorized. The goal today is not finding the solutions. We are establishing a mathematical thought process for finding solutions. We are saying, here is how we're going to do it. It's about the thinking and the process, not the solution. The thinking and process we will use are built on understandings developed in other lessons in the module. For example, lessons 1 through 4 are all about the relationship of operations. Some of the last few lessons, 23, 24, 25, where we were deciding if a number sentence is true. So this is a mathematical modeling exercise. We're going to solve this equation. I've already told you what the answer is. It's 6. Okay, great. But we want to go through the process, the thought process, and how we can represent that. This equation shows two expressions that are equal. What are the two expressions? And what does it mean for them to be equal or equivalent? How can we represent these equivalent expressions using tape diagrams or other models? How can we use tape diagrams and models to find the value of A? So taking this kind of one step at a time here, thinking about our first question here, what are the two expressions that we have? Well, we have A plus 2 and we have 8. And we are supposed to model these with tape diagrams. And so we're going to draw two tape diagrams that are going to be the same length because our two expressions are equal or equivalent. So I have my two tape diagrams that are the same length. One of them is going to represent the 8, and the other one is going to represent the A plus 2. So we're going to label the first tape diagram as 8. Now it doesn't take too much to think about what we're going to do on the other side, but let's go through it real slowly, one at a time. This second expression has two parts to it. We have an A and we have a 2. I'm going to put a 2 on here. And then I'm going to put an A on here. I'm showing that these two things are added together. Now some people ask, well, does it matter what order you put them in? Well, it is addition, which means that there is a commutative property. I can change the order and it will have the same meaning. So I have my 2, and the remaining part of the tape diagram I can represent with an A. But then I want to figure out, well, what is the A equal to? Because remember, we're looking for a solution. What number can I replace this variable A with and make this equation be true? Well, we can compute the difference here. We can do a little bit of math. My tape diagrams are the same length, so I can say that this piece here is 2, which means this piece here is 8 minus 2, which I know is 6. And this piece here and this piece here, so this top piece and this bottom piece are the same length. So I can say that A is equal to 6. And the next couple of slides we'll kind of walk through this here. so I've got a 6 there. Now, there's a couple of ways that I can come up with that. One of them is the way that lots of students do it. Well, I just know that 6 plus 2 is 8. But I want you to see the thinking that I did here. I said, if this piece here is 2, then this piece here is 2. Which means this piece here, this 8, isn't 8 anymore. It's 8 minus 2. Which means that this piece down here is 8 minus 2, which means it is 6. Just double checking, make sure I haven't skipped something. Okay, so we're going to draw another set of tape diagrams to represent a plus 2 equals 8. So here's a plus 2, here's the 8. And I've already been through this, but I'm going to show it to you yet another way. I've got 8, I've got 6 plus 2, and I've got a plus 2. And they're all equal to each other. So this piece here is equal to this piece here, which means a equals 6. So these three tape diagrams all represent the same value. Both parts that have a and 6 must represent the same value. These two pieces here have the same value because they're both 8 minus 2. 8 minus 2 is a, 8 minus 2 is 6. So thinking through what actually happened when we constructed the tape diagrams, and once again, this is like the third, fourth time in this lesson I'm going to show this to you. The first set of tape diagrams shows that the quantity of 6 plus 2 is equal to 8. We wrote it algebraically by saying 6 plus 2 is 8. The second set of tape diagrams shows two things. We added on an a plus 2. We saw that a plus 2 was equal to 8, but that also means that it is then equal to 6 plus 2. So the 6 can replace the a because they are equal. So we found that the only number that a can represent in this equation is 6. Therefore, when a plus 2 equals 8, the only solution for a is 6. Now we need to check by substituting. We need to say 6 plus 2 equals 8. Now I need to actually perform 6 plus 2. I actually need to do that operation. And 6 plus 2 is 8. Is 8 equal to 8? Yes, it is. I have used substitution to check my answer. So in previous lessons we discussed identity properties and how can we explain why a plus 2 minus 2 equals a using the identity properties. Well, we know that when we add a number and then subtract the same number, the result is the original number. So if I had a and I added 2 and then took away 2, I'm right back where I started. And we explored that a whole bunch in lessons 1, 2, 3, and 4 of this module. And we wrote this in a general form using a plus b minus b equals a. So how can we check our answer? I've already talked about the substitution, so I actually do a little substitution here. 6 plus 2 minus 2 is equal to 8 minus 2, which gives us 6 is equal to 6. So our answer is correct. All right, so here we go, exercise 1A. And this would be in class, you'd work with a partner, which would be really fun because you get to talk to them and you get to discuss. But if you're working at home, if you've got somebody you can sit and talk these through with, great. If not, think them through on your own. So we're going to use tape diagrams. That's how we're doing it, tape diagrams. So I've got b plus 9 equals 15. So I've got two tape diagrams that are going to be the same size. One of them is going to be the 15. The other one is b plus 9. So there's my two tape diagrams. Now I can use my tape diagrams to say if this piece here, if this here is 9, then I can carve out a piece here and have it be 9, and this piece here becomes 15 minus 9. And the 15 minus 9 is the same as b. They're equal to each other. b is equal to the 15 minus 9, which will be 6. So I can make the claim that b is equal to 6. I can then substitute it. 6 plus 9 equals 15. That's my claim. 6 plus 9 is 15, and 15 is equal to 15. There is my check. So here I've used a tape diagram and these very basic relationships to think my way through. Let's look at another way of doing this one. So here's a solution from the teacher materials. So I've got the 15, and I figured out I've got 6 and the 9. And these two are equal to each other. But then I also know that 15 is equal to b plus 9. So now I have 3 things that are equal. I've got this one, and this one are all equal to each other, which means the b is equal to the 6, which is what it's showing right here. b is equal to 6. And do a little substitution here using the identity property. 6 plus 9 take away 9 gives me the 6, and 15 minus 9 gives me the 6. 6 is equal to 6. All right, let's look at another one. So in your brain you should say, okay, 2 tape diagrams. So I've got 12, and I've got 8 plus c. Now I know that if these 2 tape diagrams are the same length and this piece right here is 8, that this one right here also has a piece that is 8, which means that this piece is 12 minus 8, which means that this piece is 4, which means I've got c plus 8, and c is going to be equal to the 4, which is equal to the 12 minus 8. So I've got 8 plus c. Well, I'm going to write it as c plus 8. And I take away the 8. So c plus 8, take away 8, and I have the c. And then up here, I've got 12 minus 8. So c plus 8 minus 8 is c, and 12 minus 8 is 4. And I've got right here that 4 is equal to 4. Now you'll notice that I go through my tape diagram slightly differently each time. However, what is the same each time is that I'm following good mathematical thinking. This is equal to this, therefore this is true. So let's look at another example from the teacher materials. They started out with the 12, and they had their 8 plus their 4, and then they've got their 8 plus their c, and they're saying that all 3 of these are equal to each other. And they say all 3 of these are equal, but then they compare the 8 plus the 4 and the 8 plus the c. And they say right here, these 2 pieces are the same size. c is equal to 4. So we've got the 12 is equal to the 8 plus c. 12 minus 8 is equal to 8 plus c minus 8. So I subtracted 8 to get to the identity of the c, and subtracted 8 there to keep everything nice and in balance. And I've got 4 is equal to c. Okay, now this one gets a little bit tricky. It's not addition anymore. Here we have a subtraction. I'm going to have 2 expressions that are equal to each other. Now on one of them, I'm going to take something off of it to get to 7, which means, so I've got 7 here, but I've got a number that I had to take away 5. So it was bigger to start with, but I took 5 of it off. And when I was done, I was left with 7. So this top part here is d minus 5, a number that I took 5 away from and was left with 7. So when we look at subtraction problems with the tape diagrams, we need to switch our thinking just a little bit here. After taking away, I was left with 7, which means, using the identity, if I had d minus 5, I need to have d plus 5. So I took the 5 away, but I have to add it back on. Got to get to that greater number. Now, as we think about that, that means that I've got a 7 here. That means that this is a 7, and that this is a 5, and that this altogether, it isn't d minus 5, it's actually d, because here's the 5 that I will take away to have what I've got here. So I have a number that if I take away 5, I am left with 7. And 7 is equal to this number, 7. 7 here, d minus 5, the 7 here, but I have to build my way back up to the d, which means on my 7, I need to add that 5 more. On this side, I need to put 5 more on so I can get back where I was. All right, let's look at their illustration. So I had d, and I had d take away 5 was 7. So all of it together is d. d take away 5 is 7. But I add the 5 back on because I need to get back to 7. If all I have is the d minus 5, I never have the full d. I need to add 5 on so I can get back to the full d. So here's the 5 I added on. Here's the 7 that I had originally. Combine it all together, and I get the 12. These subtraction ones require us to think a little bit differently. So here we are back to an addition one, because of course we looked at a subtraction one. Okay, here we go. So I've got 2 tape diagrams. This is addition. So my total is going to be 20. And my other expression is I've got a number that if I add 12 to it, I'll get to 20. And I'm going to connect across here and say this is 12. And this is 20 minus 12. And this is e. So e is equal to 20 minus 12. Or I can think of it in my identity properties. E plus 12 minus 12 will give me the e. So e plus 12, take away 12, leaves me with 20 minus 12, which is 8. And I know there's yet another way that I'm thinking of my tape diagrams. I had e, I added 12 to it, I then took away the 12 to have what's left. Look at the example here from, teacher materials don't even have an example for me to look at. All right, so I'll walk through a little bit more carefully here. So I had 20, and I've got 8 plus 12, which is 20, and that is the same as e plus 12. So e is equal to 8. So I've got e plus 12 minus 12, which leaves me with e. And if I were putting this on a balance, the e plus 12 was equal to 20. If I take away 12 on this side of the balance, I have to take away 12 on this side. So I have e and 8 are equal to each other. All right, here we are back with one of those fun little subtraction problems. So I've got a number that I am going to call f. And it says I'm supposed to take 10 away from f, so I'm going to cut some of it off. When I'm done cutting off, I'm going to have 15. So this number right here is f minus 10. So here I have f minus 10 plus 10. F minus 10 plus 10, which is going to get me to the f. Here, if I want to keep things equal, I need to add that 10 more on. So I've got 15 plus 10 is 25. So that's a different way of thinking of it than I thought the first time, but both of these ways are mathematically sound. They're okay. You don't have one that is more right or more wrong. What matters is the thinking. I can look and say that I had a number, f, that I took away 10, which left me with f minus 10. And f minus 10 is 15, so I had a piece here that was 15. But if I wanted to get back to the f, I had to add 10 on, so I added 10 on. And f is equal to 25. And I can substitute that. 25 minus 10 is 15, and 15 is equal to 15. I've substituted and performed the operation to check. So I've got a number g, and I'm going to take away 8. Which means that this is g take away 8. And it tells me that g take away 8 is going to be equal to 9. So if I look at my first tape diagram here, I've got g take away 8 plus 8. Down below here, if I want to stay equal, I need to add on 8 more. So I've got 9 plus 8. Now my first tape diagram and my second tape diagram will be the same length. My first tape diagram took me to g. My second tape diagram took me to 17. G equals 17. And I can check. 17 minus 8 is 9. 9 is equal to 9. Check. All right, so looking at our closing here, John checked his answer and found that it was incorrect. John's work is below. What did he do incorrectly? So he's looking at his work, and he had this equation. He had h plus 10 is equal to 25. So he's got a 25 here. He's got a 10. Bring the 10 up. 25 minus 10. So h should be a 15. So looking at his work here, he said he had h plus 10, and then he added this 10 on instead of recognizing that he had to take it off. His error is right here. Instead of saying here's the 10 and we have to subtract it, he said h 10, 10, he added them all together. That could be a problem. John should have subtracted 10 instead of adding, because we're trying to get the identity of h. h plus 10 minus 10 leaves us with an identity of h. If I do h plus 10 plus 10, then I've got h plus 20, and I still don't have the h. So looking at teacher material tape diagrams, I had h plus 10 is 25, and he did 25 and he added 10 more, so now he's got h plus 10 plus 10, when what he was trying to do was get back over here. Instead of taking off this 10, he added more on. So why do you think the inverse operation to calculate... Why do you do the inverse operation to calculate the solution of the equation? So why, if we're doing a number plus 3 equals 5, why am I doing a number plus 3 minus 3? Why am I doing the inverse of addition? Why am I adding on a subtract there? So stop and think about that. Why do we do that? And hint, 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 identity properties are a really big deal. When we do the inverse operation, the result is 0. So using the identity property, we know any number added to 0 is the original number. So if I have a number and I add 3 and take away 3, I'm right back where I started. These two things right here, a positive 3 and a negative 3, are going to make a 0, leaving me with just the number. So in a tape diagram, we've got h plus 10, and if I want to get back to just the h, I will have to subtract this off. Keep skipping through things. So hopefully you are feeling pretty confident that you can solve a one-step addition and subtraction equation by relating an equation to a diagram. We are tape diagramming. Yes, you must use them. Okay. I can use substitution to determine if my solution makes the equation true. I can take the solution I find, substitute it back in, follow the order of operations, and say, yes, it worked. Or I can substitute it in, follow the order of operations, and say, I must have done something wrong because it didn't work. So substitution to check is an important step. It's a way for verifying the accuracy of our answer. All right, so I can use substitution to determine whether a given value makes an equation true. We worked on substitution. I can write and solve equations. Now at this point we are solving equations. At this point we're not to the real world problems, but we are getting there. So this concludes Module 4, Lesson 26. Make sure that you go back and double check anything you don't feel comfortable with. Make sure you reach out to your teacher if you have questions. Make sure you complete your problem set and your exit ticket.